Well, this is chapter 10, our final chapter. In here, we're going to talk about a few things about just controlling the test procedure. Once again, we're wanting to produce good and accurate results. On page 184, third paragraph down, for each test that is performed, there is a common set of concerns about the analysis that should be answered to the satisfaction of both technician and the person who uses results. These concerns are as follow: the ability of the test to actually measure the desired parameter in the sample, how close the results are to the actual amount of analyte in the sample, and whether the same result can be attained repeatedly on the sample, and the lowest level of the analyte that can be detected in the sample, and whether the detected parameter is actually in the sample. We want to know all those when we are trying to figure out our results in the sample. We want to make sure it's close. We want to make sure it's repeatable. We also want to know the lowest level that can be measured. And on page 185, it says, bottom paragraph, the combination of quality controls performed in the lab, along with training, facility, instruments, supply management, sampling techniques, and containers, and anything else that affects the ability of the laboratory to produce reliable data is called the quality assurance program. Hopefully, you have a quality assurance program at your lab where they have SOPs, which stands for standard operating procedures, that tell you how to do every test, right? That's important. Um, that someone's went before you, they've selected out of standard methods the test method. They have outlined that how to do that with your particular meter in that lab, so that you as an operator could go in there. Like me, I do maintenance mainly, but when I go into the lab when people are sick and I have to pick up there, the standard operating procedure is how everybody in that lab is going to do that, right? How, I'm going to inventory the samples the same way that the lab guy receives samples. When I open up a sample, I'm going to put open 3/2 of 2025. When I set up BODs, I'm going to set them up the same way. My, you know, I'm going to chart my um, chart or record my slope for the pH meter, or record a barometric pressure with my dissolved oxygen meter. So all those things should be the same regardless of who's doing those. And that's called a quality assurance program. Some places have just one person. That's their whole job, is to make sure that, you know, we're giving quality results. On page 187, um, the technical term for the closeness obtained results to the true value of a target analyte is known as accuracy, or the sample is accuracy. So turn over, I'll read you the definition on page 189, second paragraph. Precision is the term given to the ability to repeatedly generate the same result from the same sample. It is the measure of the width of the distribution of results around a central value. Precision is measured in the laboratory on a daily basis by analyzing sample duplicates. So I know in our laboratory, I may run off a pH meter, and I've talked about this before. I might run off a pH sample and then put another sample out of the same bottle into a different flask and measure it, because I want to make sure that I am being precise. 191 shows a good pictorial of this. So I don't know, maybe some of you have shot arrows or archery. Um, so the bottom, well, the top, you want highly accurate, highly precise. So in the bottom picture, you have low accuracy. So you're hitting low to the left of the target, but you're highly precise. It's grouped um, in a you know tight cluster. On the top, you have highly accurate but low precision. So you're accurate, but you're not hitting in the exact same place. We want precise and accurate in the laboratory samples. One way we can do that is with matrix or duplicate samples or spiked samples. Um, Page 194, laboratory contamination is determined by the analysis of the reagent blank every time a sample analysis is performed. A reagent blank is a sample of analyte-free water that is taken from the entire analytical process and analyzed as a sample. So that's just another check to see if maybe you didn't wash out your bottle and you got chlorine in it. And you ran a blank and it popped with chlorine, and you knew that you were not supposed to have any chlorinated water in there. Well, maybe you rinsed it out with not laboratory pure water. Maybe there was a residual chlorine in there, and so it would show up as contamination or chlorine. A reagent blank is not the 0 point of the calibration curve. An absorbent blank is sometimes used to set the background absorbent on the spectrometer to 0, but is not a substitute for a reagent blank. So when you calibrate your meter, and maybe I'll bring one in and I'll show you. You zero it out, but that 0 is not a calibration uh, control. Sources of laboratory contamination, this fourth paragraph, can be exercised in ingenuity to find the source, particularly in the contaminations intermittent. Sources of laboratory contaminations have been documented, including air fresheners, perfumes, technicians' dirty hands, rubber gloves, soap. I mean, all those things, fingernail polish. That's why you don't eat or drink in the lab. It's because that could contaminate uh, your your samples. So what's a batch sample? On page 195, a batch is defined by the EPA and most other federal and state regulatory agents as a set of 10 to 20 samples that are a similar matrix, reportable under a similar regulation, and processed as a group with a single period of time. The minimum quality controls that are performed with each batch consist of a reagent blank, a calibration verification, sample duplicates, and a matrix spike. So in a batch, you would do all those quality control measures to make sure that that batch is accurate and precise with its data. Hope you enjoyed this last chapter. Hope you have a good rest of the semester, and text me or email me if you have any problems. Thank you.